So, good afternoon, everyone. So, a little about me. I am the co-founder and operations of Fastly, which is a content delivery network. I was formerly an operations engineer at Wikia, and I've been doing consulting and Linux work since '94, so a rather long time. So at Fastly, we are a content delivery network, which means we put servers all over the world, and we act as an HTTP proxy and cache, sitting and allowing users to get content and move content closer to users. We've got quite a few you've probably used before and know about. And we generally focus on making the web as fast as we possibly can, focusing on low latency delivery and just being fast. So, when it comes to looking at networking, HTTP, TCP, our end goal is to make best use of the limited resources we have. We're always going to be computationally limited. We're always going to be bandwidth limited. We're always going to be memory limited. The goal is to figure out how to make best use of these so that our users are not impacted. So for the focus on this talk, it's Linux. Everything I'm doing here is showing Linux. I put this slide in because at some conferences I go to, they're not necessarily Linux related, and they don't necessarily like it. So in looking at HTTP, we're looking primarily at very small HTTP request response cycles. As a business, we actually don't cache anything larger than 100 megabytes, so we really do look at small things. We have some users that do more header bytes than body bytes. So we're talking, in a lot of cases, very small cycles. And if you look at your HTML usage, even though the overall size of the page loads have been going up over time, the average object size is still fairly low. HTML, CSS, JS, these things tend to be fairly small. This isn't a deep dive into TCP, just enough to get you by. So, start with the accept loop. So this is where your application talks to the kernel and the boundary between the two. So a client sends the traditional three-way handshake. Client sends the send. The kernel then hands this into your server. The server decides what to do with it by calling accept. The kernel then sends a send ACK back to the client, and the client sends the ACK. And now we actually have a session. So the problem is, what happens when your application can't respond to these things fast enough? So you get a backlog. So you have all these connections that you're allowed to have in a send state, and when you're out of them, the kernel just drops them on the floor. This is really bad. The clients are going to wait. So they'll send the send, and they'll just sit there waiting, and then 3 seconds later, they'll send another one. Well, if you look at the performance data as correlated to what happens when things go slow like this, they kind of go away. Nobody has the patience for these things. Even a few hundred milliseconds or even tens of milliseconds, users start to get to notice and get annoyed. So every time you're hitting one of these overload states, bad things happen. So there's a few tunables around here. Looking at the numbers you're allowed to have, the numbers you're allowed to have outstanding. The kernel default value is fairly small. These things actually don't take up all that much space. There's an undocumented max, though, of 65,535. If you violate this, things go really bad. So what happens is there's a derived value from this, the max number of synapses you're allowed to have in flight. So if you overwrap this, you get this nice big send queue, except the number of synapses you're allowed to have in flight drops. So now you can only have, I think it wrapped around to, and the default ended up being 10. So we hit this in a very bad way. So some of our machines, the ways they're connected very close to the internet in that there's no load balancers or anything in front of them. So BGP is actually the only way we have to control whether they get traffic or not. On a high value service, this means it goes from 0 to 10,000 requests per second in a flash. So we want to be able to absorb that initial spike and then deal with it without having to send those resets. So we set this to a nice big number, and then we were dropping 700 per second on the floor. It was really bad. Luckily, that user wasn't performance sensitive in that way, so when it happened, everything just happened, loaded asynchronously, and they didn't care. And another problem with this is it's actually a linear scan in the kernel. So as these numbers get bigger, the number of sockets it has to scan, so under load, your CPU cost of figuring out which socket to wake up next gets longer and longer and longer. So it's not actually ideal to set it really big either. There's also another part of this that you don't just set these values in the kernel. The kernel sets what the maximums are allowed to be. Each application then has to request how long they want this backlog to be. A few different Nginx and Apache and such set to 511, which has some magic byte or magic boundary value. MySQL sets it really, really low. If you look through the forums, you'll actually see a whole bunch of posts of the MySQL and PHP community self-soothing each other very wrong and having no understanding of why all these connections are dropping on the floor, why their MySQL connections are taking forever to establish, why. Because you look at like PHP does not have a connection pooling library. So every individual thread request that comes in will open up new database connections. So if this starts happening, your app starts timing out and bad things start happening. So you'll notice a theme throughout this talk that I'm going to tell you repeatedly: run newer kernels. This is one of the very big reasons why. There's a feature Google added in 3.9 or got accepted in 3.9 called SO reuse port. So normally when you would start up your listener, you would start up one thread actually has the accept socket, and it would take those in and deal with it. If you started up a whole bunch of them, it would work, but the kernel would actually send them all to the very first one that registered. The others would never actually get any of these. So when you're under attack, when you have a SYN flood attack, what happens is your ability to handle this and generate syntax becomes limited by a single core, which kind of stinks. We had a DDoS a while back where it was unusually successful, and we started looking at why, and it's like, well, we thought we could handle 500,000 of these per second per machine, and it was only 200,000. Started looking into why. 2 weeks later, a whole bunch of time spent with perf, we discovered that there were a number of things. It was 14 lines of code in the end to get us from 200,000 to 5 million a second. Our Apache tree does have this patch. It's like a one-line patch to Apache and a few other things, but it makes a huge, huge difference. Google's perspective when they released this patch was our DNS servers went from handling 50,000 requests a second with some loss to 80,000 with no loss. And our view is, hey, we actually have never even benchmarked the performance characteristics. We only cared about our DDoS handling abilities. Turns out there's actually a few other things in there that were problematic, like the multipath routing code had some issues, and there was, so the network drivers. If you've ever looked at modern network hardware, it has this interesting thing where every CPU actually has a send-receive queue coming from the network card. So a packet comes in, it gets hashed to one of those queues. The kernel was then hashing it again to an accept socket on a different thing. So in NUMA architectures, which is pretty much every modern PC at this point, there's memory belongs to a socket, a core. So if you bring it up on one, raise the interrupt there, and then send it to another one, you're losing thread locality. That was a pretty minor thing. I'm not sure if that one will get accepted upstream or not, but it's out there. I don't think I have a link, but if github.com/fastly, our kernel tree and Apache tree and a few other things are up there. So that was a big thing. So I'm going to take a little bit of a detour here and focus on some other things you can do under DDoS. How many of you have ever had to deal with a DDoS? So you know you're generally screwed, right? So you talk to your upstream providers, and they're like, yeah, we can null route you. So the choice is either all or nothing. So you start looking at how these things. So being a web service that doesn't currently do DNS, our main attack is the send flood. So this is a resource exhaustion attack, as pretty much all of them are. And as most of them, they tend to be much cheaper for the attacker than the target. So the client sends the send, bogus address, you try to respond, there's nothing there. It's just holding these slots in memory. So running out your memory and your computational time to go over this list. So we have send cookies that do this. So the send cookie. So when that backlog gets full, these sends coming in, you do a little bit of computational work and send a challenge back. And if the client's a legitimate client, they'll process this and have that little cookie and send it back, and you'll say, hey, that's a legitimate request, let them through. It does have a performance impact. So for a long time, There was confused advice whether you should turn these things on, turn them off, which performance optimizations in TCP worked and didn't work under these conditions. So we decided to go actually look at the code and see what it is. And the main thing it disables is large window support. So what that means is the large window support allows you to scale the amount of bandwidth that an individual client uses much faster. It overloads some options in the TCP header. This is a big issue. This is a reason to get your parents off of Windows XP. So Windows XP has a very small client-side buffer. So say on your average DSL connection with, say, 40 milliseconds of latency, they're actually limited to about 4 megabits of throughput on that link. Kind of sucks. So now, when you get into these overload situations, all users are in this condition. Not so great. So, how do you deal with these things? You want send cookies on, and you want to be alerting when you start seeing these things occurring. It is, you've seen the log spam, send cookies are being sent, do these things. It's a pretty good indication something's broken. Whether your backlogs are just too small for the application or what, but it's an issue. We've noticed a lot of these attacks have a very distinct signature, such as everything that's not legitimate we would see was coming in at the same window size. So it's kind of a pain in the butt to write an IP tables rule on a SYN window size, but it's easily doable, and it helps. You still run into a situation, though, that you may become interrupt limited, because you still have these things coming in, it's still coming into your entire network stack, and it's a problem. So there are hardware filters, whether it's your upstream firewall, or I'll show you the cool stuff next. So hardware. So I'm kind of lucky in that I largely don't have to deal with the cloud. I have lots and lots of very high-end hardware spread all over the world, so I get to do fun things. So as I said earlier, you have these queues. All modern hardware is multi-queue. If you're using hardware that isn't multi-queue, you're probably getting screwed pretty badly. Like the Broadcom BNX drivers, the pre-BNX2, was all single queue hardware. That single queue on modern hardware, you only get around 20,000 packets per second of throughput in a lot of these cases, and it kinda isn't that great. The other thing is all these queues get bound to IRQs. So if you're running IRQ balancing, the kernel's now trying to swap these things around. So you have this hashing coming in, the kernel then trying to move these things around, so you're consistently losing locality and things are going bad. In the Intel driver package, there's a nice little script. So if you go to their page, download their driver build off of their site, there's a little IRQ balance script in there that will allow you to do static assignments across these cores, so you can kill off IRQ balance. Because if you just turn off IRQ balance, everything goes to core 0, and that doesn't work particularly well. This hardware also has packet filters. How many of you knew that your network cards have packet filters built into them? They're kind of nice. So they're not very wide, they're not very smart, and they're not stateful. But when you start using them, now you don't have any interrupt load because it never makes it into the OS. So if you have a signature, you can't necessarily map it, but you can fill in, hey, this AS number behind this subnet is attacking me. The amount of legitimate traffic I'll use by blocking this really isn't that large. So you can kill it. Like I said, when you're under attack, all you're trying to do is mitigate these things so you can start serving as much legitimate traffic as you possibly can. They also have hardware flow directors. So not only can you say these packets come in, but you can do a little bit of direction with those packets. So you can use the traditional CPU set mechanisms and say, I'm going to put these things on this single core, and I'm going to use the rest of the cores to balance the incoming traffic. So if you have bad things happening, you can still get into the machine. You can extend this even further up the line to your switching gear and use quality of service and give yourself a little more headroom, as well as doing nice values on the machine to keep the system responsive. Because if you can't get into the machine, you're never going to get out of this situation anyway. And also things like BGPD. If BGPD can't get traffic, the hold timers are going to expire, it's going to yank the routes, and you're off the internet anyway. So that's kind of bad. We, at a Nanog presentation a few years ago, and it's a patch we've got in our own kernel tree, the problem with the flow directors, though, is once you start using them, you have to be very explicit and start programming everything. So it's kind of a little bit annoying. There's a patch to make core 0 special. So core 0 will never get an interrupt raised on it unless something's explicitly assigned to it. Do you have a question? Oh, OK. Yeah, feel free to ask any questions. Stop me at any point. So they're kind of cool bits of hardware there. In practice, this worked out extremely well for us and made life under attack much, much easier. This hardware also has some special capabilities. So TCP processing is traditionally done all in software, so you can offload part of this to the hardware engine. There are two types. There's full offload and partial offload. Full offload is probably a really, really bad idea for most use cases when you're connected to the internet. Internal running, say, iSCSI between two machines in your local data center, probably not a bad idea. But on the internet, you may end up having to deal with retransmits and such. So your buffer resources on your card may not be able to handle that particularly well. It's also very much something you can't inspect. And because parts of the kernel need to know what's going on, you may not be able to do as much with IP tables as you want. Your quality of service filters may not work as well as you would like because you just don't have control over whether the buffer, how large the buffers are and how those things actually work. So we have partial offload engines, which help, but they're not a panacea either. So the first thing is large receive offload. So if you're getting a lot of incoming traffic, you may not want to process those all the time. So every packet coming in is going to get raised to the interrupts, and now you're crossing that boundary between the network card into kernel space. HTTP doesn't necessarily follow that pattern, so it's not as interesting for these LRO engines. And they also, in several brands of NICs, don't do IPv6 anyway. So if you're on the public internet, that's going to be a problem. The next one, so you have LRO, and then you have GRO. It's a little bit better about these things. It's not focused on these large things. Has this idea of what a safe packet is that can be merged before handing off to the OS. Might help you. We're not actually using it in practice, but it's something that might help some people. Is not a horrid thing. There's another one called segmentation offload. So this one actually can be really, really useful for for large response objects. So instead of having the kernel take your data out of your application's buffer and slice it up into little 1,500 byte packets or whatever your MTU is, and then handing off to the NIC, it sets a template for that flow. And then it just copies it a whole bunch of times by filling those in. So it can be really, really useful for large flows. Sadly, doesn't describe the web as far as we see it. So not so much. It's disabled everywhere within our network. Another feature they'll do is handle the checksumming of the incoming packets for you. Again, with small packets in our rates have not been something we've seen really any benefit for. Something worth testing, might be good in your environment. Not something we've seen useful really at all for us. Another thing to watch out for is the bonding driver in the kernel. So, yay, you have great multi-queue hardware and puts a thing, but when you apply the bonding layer, you end up with a single queue. So now you're forcing everything through there. Your rate at which you can actually send packets is really, really low. The Mozilla guys reported that when they did bonding, they were able to get a max of about 20, 30,000 packets per second through their network cards. Not really great. Miracom has some good hardware that will hide all this from you, put it down to the LACP layer, and you just get a 2 gigabit or 20 gigabits upstream link. Okay, whatever. We don't use any of that. We actually use multipath routing, which is not something we see a whole lot from other people, because I've seen all the tools that like run IP route show and collect telemetry data completely broken. Like our default gateway in Chef becomes the word next hop. Really useful. We did find some minor bugs in there around some locking. We've got some patches, hopefully going up to the kernel fairly soon. It also doesn't necessarily address the inbound case, but if you're running capable switches, equal cost multipathing on the switch works fairly well. Another aspect to this to keep in mind is TCP Slow Start. So when you start communicating with a client, it doesn't know how much bandwidth there is between you and the end user. So it tries to fill that pipe slowly. So the original TCP standard did not have something like this. It would just like fill up a big buffer and send, but that kind of broke. When you hit these limits throughout the entire thing, nothing can ever get through these pipes because nothing ever backs off its sending rate in the face of congestion, and everybody just kind of falls down. So we've had this mechanism for a rather long time. So the way it works is you have what's called the initial congestion window. So the server will start off and send a few number of packets and then wait. So when the client sends that very first packet back, it unleashes more. So it sends twice as many. So it tries to grow on an exponential limit up to whatever the bandwidth, whatever the maximum bandwidth for that pipe is, and then back off a little and try to keep a steady state there. The problem is if you have a drop packet while you're doing this rise, it just drops through the floor and is very aggressive about backing off and then coming up slow again until it gets into what's known as congestion avoidance mode. So once it's hit that peak and it's starting to back off, now its response to these events is much slower. So Google did a lot of research recently on how big that initial burst should be. So historically, that burst was 3 packets. So that bounded, based on your latency, the amount, how fast that connection would fill and rise. So especially if you're dealing with HTTP, small request response cycles, you didn't have all that much room. So if you're doing a very small request, having to wait for slow start to build up kind of hurt. So they proposed, I think, to the IETF to raise the standard for the default up to 10. So if you're running a newer kernel, 2639, it's pretty old at this point, you're already there. You don't have to worry about it. If you're not, this is actually set as a path metric. So in the kernel, a lot of these things are defined on routes. So you set it on the default, it's just going to go. Or you could override it for specific users. It actually gets a little even better than that. In the kernel now, there's something called metric saving. It's been there for a long time. By default, it's not enabled. But what it does is it watches all of these connections over time and stores, last time I talked to you, hey, you were really close and had a really high bandwidth, low latency link. So the congestion window on our last conversation got up to, say, 100 packets. So let's just use that next time I talk to you. The buffer that it keeps around for this is very, very small. I think in practice, I've seen it in between 2 and 3 minutes. So it doesn't keep these conversations very long, but you have them. The other cool thing about this is in older kernels, it was visible via IP route cache. In newer ones, there's a newer structure. I don't know how many you know, but the routing cache is now gone in Linux as of 3.6. So this is where that data used to live. They've added a new structure in there called TCP info, which is really cool because now you can look at, over this time period, all the conversations that the kernel has had with all these users. So it captures things like the detected round trip time. So when you sent that SYN, how long did it take or you sent your SYN ACK, when did that ACK come back? So you have this idea of what the path characteristics are. It also captures like the throughput detected on that and the slow start threshold values and all of these very useful things. But it was kind of dangerous for a while because of how reactive the kernel is, the slow start algorithms are. When things go bad, because these are path metrics, you could end up penalizing a whole bunch of users behind a path. So around 3.2, Google also contributed this thing called proportional rate reduction. So it's a little less aggressive about backing off, and it's quicker about getting back up to the previous detected value before congestion. And it makes this whole process much safer and much less likely to penalize users because, hey, that person's on a congested local Wi-Fi network and things went bad on their end. So instead of penalizing everybody else in that /24, it just continues on. So kind of useful. So the other thing you have to keep in mind is buffering. So throughput equals buffer size divided by latency. So you have these buffers. Because you can only see so many packets in flight at a given time, the round trip time defines the amount of buffer space and the round trip time define how fast you're ever going to be able to send to a user. That's why XP is so painful when you have these very small buffers on typical internet latencies. They really can't get much throughput. So with a 16 megabyte buffer at 50 milliseconds, you get 320 megabytes a second. That's pretty reasonable and going to work fairly well over the internet. Yeah. So you have a few tunables that go with those. They're set 3 values. Those are what we're actually using in our production network. They've been cargo culted, but I never see anybody explaining why those values are what they are, why that max value is appropriate. So for an average internet latency, so as a CDN, we have nodes all over the world. So each node is usually talking to people very, very close. So these buffer sizes are pretty reasonable. The other thing to keep in mind with these buffers is what happens when a provider upstream from you happens. So we talked about retransmits on the client side. We have the same thing on the server side. So say there's a congested peering point that you're connected to, something happens, you need to be able to hold all of these packets in memory until that timeout expires. So your memory usage can spike very quickly. We've hit this pretty badly. So our current node profile is 768 gigs of memory with 18 terabytes of SSDs that are M-mapped into main memory. So it's page cache. So being a cache, we're very, very lazy about ever writing things to disk. So when you have one of these very intermittent memory spikes, you suddenly need to free up a lot of memory in the page cache very quickly. So kswapd gets involved and you start flushing the page cache like mad. Now your I/O system is getting a whole bunch of pressure writing off the disk, and the whole thing kind of tends to stall. So not ideal. We've been working with the kernel devs on that one too. There's a lot of things to be fixed in kswapd. So the next thing to pay attention to is time wait. So after the server has closed the connection, it's going to keep some housekeeping data around on this thing. Just because network events happen, you want to keep this data around. And there's a timeout. If I remember correct, it's 120 seconds by default. It'll keep these things around. So if you're doing high connection rate services, you'll collect a lot of this garbage. And if you don't have any more of these available, you have a high watermark for how many you're allowed to have. If you don't have any more around, the kernel won't take any more connections. So yeah, the default's 2 times the fin timeout, so 120 seconds. You can drop your send timeout. Something useful in general purpose networking, but remember, we're looking at the web, very special use case. So this is something we can drop down pretty reasonably. So yes, so there are some tunables around here that say, hey, I've got these around, they're gonna die, I might as well use them again. The TU reuse one is okay in almost all cases. You can also set the bucket sizes, so the default, not particularly great, but something you can tune pretty reasonably. So if you're looking at it from the outside, if you know your connection rate, you can figure out what a reasonable value is for this without too much trouble. Now this one, though, do not use. So at Wikia, when we were moving our offices around, was also around the same time we were setting up Varnish for the first time. So we moved into this new office, and since we use our product every day because we had content editors so everybody in the office is accessing our site at once, every now and then they'd report, hey, why is it taking 30 seconds to load these images? What's going on here? And so they'd all leave the office and go elsewhere, and then we'd sit there, try to debug. It's like, well, we just built this new firewall in the office, so let's replace this. And then I'm testing, and everything works great. And then everybody comes back the next day, and it's broken. So we keep going through this, and this cycle keeps happening a week because I can never replicate the problem. So the CTO and I were in the office at the same time, staring at packet traces, and we see this thing pop up. It's like, oh, and you see these things go backwards. So the way this thing works is allows the reuse of this timestamp. So if you have a firewall, so your NAT also keeps some TCP state data around for these things. So if the NAT times this out before, if you time this out before the NAT, the next connection through the NAT is going to break. If we'd been running an OpenBSD firewall, we actually would have noticed this right away. It does some timestamp sanitation, and this would have shown up right away. So yeah, it's really great if you're doing performance testing on a local network. So I traced down how this value ended up on the Varnish wiki, because we cargo coded it from there. So where did they get this from that they thought this was okay? We never actually had a user complaint from the external side, because we were a consumer-oriented website. We would very rarely have multiple users behind the same NAT device accessing the site at once, and if it did break, they just always assumed, hey, my Wi-Fi's screwy. So we never actually saw it. So I figured out that Willie Thoreau, when doing work on HA proxy, had this in his benchmarking scripts. And people saying, well, that's how you make HA proxy fast, so this is what you must be doing. And it was that repeated over and over and over again. And people kept using it, and then things would break. Yeah, that was a week of my life I'll never get back. So another aspect to think about is how the protocols themselves interact. So HTTP takes 4 round trips to establish a connection. The TCP handshake plus the GET going back to the site to create that initial connection. SSL actually takes 6. So when you have these round trips, the amount of time it takes before a user actually starts getting content starts to matter a lot. So especially here in Australia, I should have updated the numbers for Australia. You guys talking to US websites hosted out of EC2, this really stinks for you. These things. So this is why CDNs exist in some aspect, even if we're just opening a connection to the back end. Another thing to keep in mind is the SSL handshake. If you're running event-driven servers, this is kind of interesting. So under load, one thing that happens is your event loop. So event-driven servers are great if everything's non-blocking. Problem is, SSL handshakes are a blocking operation and will take 1 to 10 milliseconds. So if you have a very high handshake load on your web server and you're running an event-driven model, you'll go this boom. As your computational time gets longer and longer, your event handler starts freezing for longer and longer periods of time, and your performance just absolutely drops to the floor. So threaded can be useful, but then you have thread stacks and keepalives. So if you can get it closer to your users, that's great. So ELBs, sometimes you can use an Amazon location closer to you and forward remotely. Most CDNs will do this. We, of course, do this at Fastly. Akamai sells this as their DSA product. Even if you're not caching near the edge, holding open a connection to the origin that does not have to do that handshake process. So if we can keep a connection open to your web server, so when that connection comes in, we'll do the handshake very close to the user, have this very quick process, and then we've already got a connection open, so it's just 1 round trip to send the request back to get the content. Kind of useful. So I've actually blown through these things very, very fast. So the basic advice is upgrade your kernel. The Google guys in particular, Dave M at Red Hat, have been doing fantastic work. Google has been helping push the state-of-the-art in TCP itself forward as fast as anybody reasonably can. If you see their quick protocol, it's not happening anywhere near as fast as they'd like. The congestion window is that very first thing. If you can fit your request response cycle, especially if you're doing SSL, you want to get your certificate in that very first. So if you start having to fragment or having to split your certificate over multiple packets, and that's going to add even more round trips. So that's bad. The backlog and time wait, they're critical. Maybe you've cargo-culted a script or pulled something, but they're worthwhile to check. And the buffer tuning, out of the box, some of these things are kind of slow. I don't have any per distro values, but not all of them set them to reasonable values because they're not tuning for your workload. By default, the distros ship what's not going to break the average case. So it is worthwhile looking into these things. And if you can, move as close to your users as possible. These latency effects, some of them are just the speed of light. So what you can do to mitigate or hide latency can be highly, highly valuable. So thank you. It's been an absolutely wonderful week here. This has been my first LCA, and you guys have all been completely awesome. So thank you. Questions? Yes?
Do you think HTTP2 is going to change much of that landscape?
So the question is, do I think HTTP2 is going to change much of this landscape? Yes. In that, a lot of these problems with the congestion control windows become more exacerbated when you have multiple connections, because when you have these things, they all hit the congestion event at the same time. So all of your connections are going to be going through slow start and competing with each other to go back up to that thing. So they're each going to be hitting individual congestion events. So having a single TCP connection that these things are multiplexed over will allow slow start to work much better, get nearer the edge, and respond to congestion events quicker and in a more consistent manner. That being said, we don't support SPDY or HTTP2 yet, but it's on our eventual roadmap once it's been ratified. More questions? Yes?
Just plug for WAN-M or similar tools that will emulate loss, because most ISPs wouldn't understand congestion if they were with correct that.
So the comment was WAN-M, I think was the tool?
Yeah.
So
you could do it raw with Linux TC, or you could use something and keep the sanity you'll lose.
So tools for simulating these things, so the TC tool and the WAN-M for scripting those tools to allow you to set up and test these conditions is WANM, I think?
EM.
EM, sorry. The EM tool, so the emulator device, and being able to set path characteristics. I've seen a lot of tools over the years for simulating these things, so you can say, on this link, it's constrained to this many bits per second, and we'll have this loss profile. What was the name of the simulator stuff? There's actually a lot of really useful tools for building. There's this Python framework, I can't remember the name off the top of my head, that allows you to specify a whole bunch of nodes and the topology between those nodes and run scripted tests on those nodes. It was actually a really brilliant little tool, but I can't remember the name off the top of my head. Any more? Yes?
Do you have any advice for measuring the effectiveness of different of these options, particularly outside a lab environment?
Retransmits. So on an average internet-connected host, you should see, I think Google says globally around 2%. Our nodes tend to talk to users very, very close to the nodes. So we see 1%, though we've got this one provider that we see around 5%, which is kind of annoying because as we pay based on a 95th percentile billing thing, they're essentially padding their bill and sucking for our users. So internally, there are very few metrics that we will page an ops person about. Number of 500 responses coming out of a data center is a big one, but the other one is the percentage of retransmissions happening in a location. So we do track these things very closely, and that's the first indicator, because every time there's a retransmit, we know a user's getting screwed. So those are things we watch very, very closely. And it's not necessarily the first hop path. It's usually this ISP, for cost reasons, is overloading their peering port, and that's something we can't do anything about. So a lot of traffic engineering work is going on our side to avoid those types of situations. Any more? Yes?
Yeah, latest kernels. You don't know whether or not our friends at Red Hat might be actually backporting some of these things into their current kernels.
I have no idea. I haven't run a vendor kernel in a very, very long time. We have found stepping out of the ecosystem and staying close to vanilla. We don't buy vendor software, so we generally don't have a vendor support channel. So keeping open and being able to work with the wider kernel community has been extremely valuable to us. And they've been absolutely wonderful. We hit this very rare bug. Took us the better part of a month working with them to track down, where we were seeing in this data center, after 2 or 3 days, we would see a kernel panic. But in this data center, it would take nearly a month. And we'd look, and the traffic levels are fairly similar. They're running the same kernel, same user space. We had a hard time figuring out what was different from these locations. What we discovered was in the data center it was crashing was in Amsterdam, and it was serving Russia. Russia has rather poor networks in a lot of cases, so the retransmit rate on average was much higher. So there was a bug in the retransmit callback timer path failing to decrement a reference count. It had apparently been there for quite a few years. We're kind of odd that most people have large core routers and load balancers and all these things abstracting the HTTP servers from the user communication session, and because we've eliminated almost all of those layers, we start to see these really, really weird problems. So that one was fun. I thought Dormondo was going to kill people at the end of that process, because it was like, did it fix it? Did it fix it? And then a few days later it would crash again, and then you go back and it's like, you never know when it's done. These long debug cycles really suck. Any more? Oh, thank you. It's been fun.